gonna go into some algorithm that we can take a look. This is not my slide. I also get it from the internet. This is something called the Dijkstra's algorithm. We're going to take a look at what is the purpose of this algorithm and how to practice on our own hands. I don't think I'm going to ask you to implement this in your in programming because you can easily find these examples on the net. But hopefully give you some chance to practice someone else's algorithm and get an idea of how to maybe just before the implementation, how to design it. So this is the person who wrote this algorithm. It's a very famous guy. Obviously, I never met him, but computer science is no more about the computers than astronomy than about telescope. It's come on, 별로 그렇게 의미 있는 얘기는 아니고. Anyway, this is the guy who come up with the algorithm. This guy just wanted to say a few things about this person. Very famous. He's the recipient of the Turing Award. It's like a Nobel Prize award for computer science. 튜링 어워드 되게 똑똑한 사람만 받을 수 있는 거의 노벨상, 컴퓨터계의 노벨상. And then blah blah blah. There was one interesting work he did was he made a strong case against the use of go-to statement in programming languages and helped to lead its depreciation. What does this mean? Can somebody translate that for me? 저 번역하면 무슨 뜻일까? Made a strong case against the use of go-to statement. Is there I don't know in C, maybe even in C, is there a programming instruction something like go to line 10? C에? 뭔데? C의 go to가 어떻게 써요? 뭐 스위치 같은 거 얘기하는 거예요? 스위치를 go to라고 얘기하는 거예요? Okay. Is that a nice idea? 난 C에서 고트를 한 번도 써본 적이 없는데 옛날 베이직 쓸 때나 쓰지 한 번도 써본 적이 없는데 Anyway, what he tried to say was go-to statement in programming language is not something that we should use. So he made it disappear in some of the programming languages. That's what he did. He made a study on that this go-to statement is poor designing of the language. So it means it disappear. Well, go-to statement in the previous versions maybe stay, but newer versions of the program, they probably kind of ignore this. go-to로 하면 나중에 되게 귀찮죠. 어셈블러를 go-to 하면 나중에 어디에 있는지 확인이 안 되는 경우가 많아요. 되게 많으면. So that's one of the interesting achievement he had in his career. Anyway, he's also known for many essays on programming. So genius, simply put. So one of his algorithm is, we're going to take a look, is as this. It's a single source shortest path algorithm. Single source shortest path problem. And he proposed an algorithm to find one. Single source shortest path. So the graph like this, the problem is, give me a shortest path from point 6 to rest of the node. Node 6. I'm going to call this as a node. This as a edge. Okay. From 6 to rest of the node in the graph, can you propose me the shortest path in this graph? Can you come up with the algorithm that reporting the shortest path? What might be the shortest path from 6 to 1? How many paths are available from 6 to 1? Just look at this graph. 6에서 1번까지 가는 길이 몇 개나 돼요? I don't know. could go this way. You could go this way. You could go this way. 그죠? You could go this way, or you could go this way. I don't know if you're allowed to repeat its path. So I like to find out the minimum cost of getting there. So single source from one point to rest of the point. The problem of finding shortest path from a source vertex V, another word for node is vertex, 동그라미 vertex, V to all other vertices in the graph. That is a problem statement that we want to solve. So without looking at, if I ask you to implement this, if I ask you to bring a pseudocode for this problem, can you give me one? 숙제가 만약에 pseudocode를 가져와라. Finding shortest path. 그럼 어떻게 해요? Let's guess. Well, it might be the natural approach, or it might be the easiest way of think of general idea. Let's draw a sketch on the algorithms that we can come up with. 어떻게 하면 될까? 6에서 모든 다른 노드까지 모든 길 값을 구하라. 그럼 어떻게 하면 돼요? 트리도 있을 수 있겠죠. 그냥 쉽게 하면 어떻게 하겠어요? 트리 막 이런 거 생각하지 말고 다 해보면 되죠. 그죠? 6에서 닿을 수 있는 모든 노드까지 길을 다 계산해가지고 그러면 닿을 수 있는 애들은 다 나오잖아. And then you try every possibility of from 6 to every other node. Maybe you pick the minimum distance among all those possible paths. 그죠? It's going to be expensive algorithm, but it might be the reasonable algorithm. It might be the not only one, but reasonable algorithm to follow. 그죠? 6에서 갈 수 있는 모든 노드의 값을 다 구해놓고 그 중에 제일 작은 거 선택하면 shortest path 아니야. 물론, what might be the consequence of doing that? You need to spend a lot of time to discover all the paths in the graph. But that's something that we can live with. So, okay. Then we understand the problem at this point. So he come up with the algorithm. The Dijkstra's algorithm is a solution to a single source shortest path problem in graph theory. Graph theory? What is graph theory? 나중에 가다 보면 there are very strange mathematics later. I don't think we're covering. It's a part of, not entirely mathematics, combinatorics and optimization. Some people study on this graph only. 이렇게 막 그려놓고 이런 거 그려놓고 what might be the possible path from A to B? How do you divide this graph into half? 이상한 거. 이런 거 하는 사람들이 있어요. 그래프만 놓고. That's a area of graph theory, but it seems to be you guys were very familiar with this area nowadays because of the SNS and etc. If you try to watch your articles and news articles and media reports, they usually bring up a very complex graph like 이런 그려놓고. 전에도 한번 하지 않았나? They give you this graph like, and then the question they ask you, who's the most popular guy in this graph? Who is the popular guy in this graph? Assuming this is one people, if they have an edge, then they have a relationship or an 일촌, like Facebook friends. And they give you a graph like this and asking a question. Give me an algorithm to discover the most popular guy in this graph. 여기서 제일 인기 좋은 친구 누가 돼야 돼? 그러면 얼핏 봐도 뭐 예, 그죠? maybe the second one. Right? So there are people, researchers, scientists, they try to work on this type of algorithms. What if I disconnect this too? These two groups have a relationship or not? Right. So they try to just study on this part only. 요즘에 하도 신문에 이런 게 많이 나오니까 원래 이거 하는 사람들이 그래프 디어리 하는 사람들이에요. 그래프 이론. 야, 저기다가 what if I ask you to write a pseudocode for finding the popular guy, the most famous guy in your SNS friends map. 여기서 알고리즘 해오라 그러면 어떻게 해야 돼? 어떻게 알고리즘을 짜오면 될까? 이게 만약에 당신이라 그러면 you 어떻게 따라가면 돼? 그냥 무작정 다 따라가야죠 뭐. Friends of the you, friends of his, also I visit, go. It's going to be also very expensive operation to find the possible path. 저렇게만 그려놔도 벌써 알고리즘이 애매해지잖아요. 찾기가 상당히 어려워지죠. 근데 luckily there is an algorithm already ready for you to use. 굳이 만들 필요 없어요. 저걸 이미 몇십 년 전부터 하던 사람들이 있어서 잘 갖다 쓰면 돼. 괜히 don't even try to outbid this algorithm. 그죠? 이거보다 더 좋은 알고리즘을 만들겠다고 머리 굴리지 마요. 웬만해서 나오지 않아요. So, work on both directed and undirected graph. However, all edges must have a non-negative edges. There are some conditions that you have to follow in order to this algorithm to work. First condition, work on both and direct and undirected graph. Brief summary of the graph. Directed graph means this. Node, vertices, directed. Undirected, no pointer between. So it can go both directions. So this algorithm work on both type of graph. 이렇게 하면 여기서 일로만 갈 수 있는 거고, 이거는 양쪽 다 왔다 갔다 하고. And all edges, the line between the two nodes, must have a non-negative weight. I could have some values in the between. Let's say the cost of going node A to B may be 10. Maybe 10. Okay. Let's say no negative values. No. Only positive values only. Why is that? If there's negative values, the total cost will be, sometimes it will be less than, 마이너스 값이 있으면 값이 줄 수도 있잖아, 그죠? So the condition for this algorithm is positive values only. So imagine that this graph, maybe 10, 5, 2, 1, 2, 1. What is the shortest path from A to B? 어떻게 하면 가장 가까운 길이에요? 10, 2, 1, 1 will be much less than 10, 5, 2, 1. You just compare a value between the two paths. That's the cost of how much it takes from A to B. I just choose the minimum cost among between the two paths that I can take. So approach greedy. So algorithmic approach for this is greedy. Simply put as you try every single path and see, and I choose the one that I like. So it's going to be, in terms of time efficiency, it's going to be taking a lot. Okay? So input to this algorithm is weighted graph, G equal EV. 지금까지 이렇게 쓰는 알고리즘 본 적이 없지, 그치? 제대로 formal way of representing the inputs and outputs. This might be the right way of doing it. So weighted graph G, so some graph G, consists of, graph is consists of two things. What? Node and edges, right? So vertices. 아이고, 여긴 edge. edge가 먼저 나왔네. edges and vertices. For all E, 아이고. 이런 걸 어디서 이렇게 쓰지? 어디서 이런 게 나오죠? Weighted graph G consists of edge and vertices. Source vertices, small v it's a set of all vertices likewise. And the edge between, let's say edges between all the edges, cost of edge maybe conditions that I have. So that's what that means. This is what I need, the input for that. And output, the output of this algorithm will be lengths of the shortest path or shortest paths themselves for a given source vertex V to all other vertices. So for some V, report shortest path. But path is what? Path is probably the sequence of the vertices. 그죠? V1, V3, V2, V3, V4. In order to go to V4, maybe I need to go through from V1, B1, B2, B3, B4. Likewise. So sequence of the vertices with the minimum cost. So this is going to be my output. This is going to be input of this algorithm. 수도 코드를 쓸 때는 참 편한데 이제 슬슬 이렇게 써보면 재밌겠죠? 이렇게 쓰면 나중에 뭐가 좋을까? A formal way of writing down this way. Maybe later it might be useful to do a proof. 증명하기 좋겠죠? 증명하기 좋겠죠? Can you prove that your shortest algorithm is actually the shortest algorithm that you found? 찾은 shortest path가 진짜 shortest path인지 아닌지 증명할 수 있나? 1이 1인지 증명하라는 얘기랑 똑같은 얘기 같죠? 그죠? There may be one proof out there, but those proofs are very difficult. I can't even explain. But they give you a brief idea on how to prove that. Anyway, this is your pseudocode, which is slightly look different from what we discussed in class. 그죠? Our pseudocode is much nicer in terms of description. It says input, output, print, but they use a much more simpler notations. I can explain some from the top. 이것도 수도코드예요. 수도코드. 그죠? It says I'm going to declare one array which is array distance of a S source vertex, one vertex. So this algorithm is from S to rest of the node. Okay? It says distance of a source to other node initially will be 0. We're gonna set it the array every value will be distance will be 0 because we haven't started the algorithms yet. 그죠? And then the next one says for all V all vertices in the graph or V except for S S 빼고 B minus S. 그죠? For all B, V 소스만 빼고 이렇게 전체 세트에서 지금 하는 S만 빼고 모든 것에서 do distance of v to infinity. 그치? 여기까지는 이해가 가죠? 처음 시작하는 거야. We're gonna set everything to 0 from that node to the other node. We're gonna put that as initially infinity. 다 무한대. So biggest number that you can find. Biggest number you can find. And then S is a sum set. It says sum set. But initially this is empty. No. 이렇게. 그 다음 또 뭐야? Q is V. So Q is another set containing every element of V. 여기 B가 다 들어가 있는 거야. And then they wanted to do that while loop, while Q is not empty. Let's do this. What am I doing inside this loop? Here I probably find that my neighbors from source node to neighbors, record the distances, and then after you record the distances, you try to find another path if there is one, and then they keep comparing the minimum ones and select ones, and then going back up again until you reach every single node in this graph. 여기서 어떤 식으로든 select the minimum one, minimum path, cost. When you're done, add it to Q. Until you cover everything. So, what's going to be inside? Maybe easier to look at the examples first. And then at the end, they just finish the algorithm, return distribution, distance array. So final output of this array will contain the cost from source S to rest of the node. 이렇게 돼 있겠지? V1, V2, V3, V4, V5, V6, V7. Assuming there is 7 node, maybe I'm going from V1. V1에서 B1은 distance is 0, 그죠? From myself. Maybe V1 to V2 is 10, 5, 2, 17, 8. This is output. From V1 to V2, the shortest path will be 10. Shortest cost, minimum cost. V1 to V3, 5. V1 to V4, 2. This is what's containing in this distance array. Let's take a look at what's going to be inside this loop. Actually, it's much easier if you take a look at the examples first. 근데 이게 훨씬 뽀대나지 않아? 수도코드 쓰는데? 훨씬 멋있지 않아요? 디스턴트 셋 막 이런 거 쓰니까. 이게 어디서 나오더라? 무슨 과목을 들으면 이런 걸 하는지 잊어버렸어요. 여러분들 그냥 정석 제일 첫 페이지에 나오는 게 뭐야? 혹시 기억나는 사람 있어요? 집합 나오지. 집합이 셋이야, 셋. 집합 나오고 그 다음에 뭐 나와? 벤 다이어그램 나오죠. 이런 거 나오지. 지금이라도 한번 쓱 스쳐보면 걔네도 똑같이 이렇게 쓸 거예요. set 1, 콤마. 똑같은 얘기예요. 똑같은 얘기. 셋이 비어 있으면 걔네도 이렇게 쓸 거예요. 여러분들 다 한 거예요. 한 건데 사실 이용을 잘 안 해서 그렇지. 그렇죠? 이렇게 숙제를 해오라 그럴까 봐. 멋있지 않아요? 훨씬 멋있는 것 같아요. 우리처럼 주저리 단어 써놓는 것보다는. 근데 상관없습니다. 수도코드의 가장 큰 또 하나의 목적은 다른 사람들과 이렇게 소통을 하기 위한 것도 있기 때문에 알아만 들으면 돼요. 복잡하지 말고 컨사이스하고 복잡, 이건 진짜 컨사이스하죠. 진짜 심플하죠. 써인 노테이션은 딱 보면 알게. 그렇죠? 내가 굳이 설명 안 해줘도 이것만 딱 줘도 무슨 소리인지 알아먹겠죠. 노테이션만 보면. 그지? 대답 안 해. Okay. This is the first example that we can go for. So this is a graph. This is a graph. It's a given graph. And I like to find a path from, the shortest path from A to all other nodes. A to B, A to C, A to D, A to E, all other nodes. Like your algorithm says, after you initializing everything to 0, and then the second line says, except the vertex, except the source, I'm gonna set everything else to infinity. 그지? I'm ready to go before I walk into that loop. And my set is initially empty. Okay. 근데 뭐 여기서부터 알고리즘 없어도 돼. So I like to choose the minimum one. Among all the infinite numbers, 0 is the minimum one. Okay. Next one. From A, there is a 2 destination you can reach to, which is 10 and 3 right away. This is edge in the between. So I write 10, 3. So next step is I choose the minimum one again in this list. What is the smallest one between 10 and 3? 3. Like pick out 3. Soon as I select C, I update my set AC. So I'm keep walking in this graph. The reason that I put C right here because I just went there. Okay, so another way of looking. I'm walking around this graph. C. Okay. So next one. From now you know that from C you can reach up to B, D, E, right? After C, you can go here. Write it down. From A to B now, 7, which is better than before. So A to B가 before was 10, but if you go through, if you go through C, then it only takes 7 right here. And then D from through C, A, C, D, 3 plus 8, 11, E, A, E, C, only 5. So this is new list. And this line, what is the minimum value? 5. Maybe I go to E, 5. Select 5. Good. Do the same thing. From ACE through ACE, through E, I can also go to, 또 어디 갈 수 있어? D, 또 어디 갈 수 있냐? D만 갈 수 있구나. D. So I calculate value 11, D again. 7 and D. Between 7 and 11, the smallest one between the two is 7. Select 7. Okay. Finally, through A, B, C, E, you can reach to D, but if you go through, 어떻게 가면 되냐? 오구. 여기까지 가는데 9, 3, 4, 2. smaller than 10, 2, smaller than any other values. So through B, I can go D with the 9, which is smaller than previous 11. This is previous path that I can go to this D. But I have only one left. This is probably the minimum value to 9. As soon as I select that, I also update that set. 그죠? Then I went through all the vertices in the list A, B, C, D, E. What happened here? Then I drop out this loop. Done. 그죠? vertices 다 갔잖아. 다 갔죠? 어구. So you're done. So this might be my final output from A to B. The minimum cost is 7. A to C, minimum cost is 3. A to D is minimum cost 9. A to E, minimum cost is 5. Cost is 5. Again, assuming there is no negative edges in the between. 여기 네게티브 들어가면 어떻게 돼? 완전히 다 꺾여서 말이 안 되죠? 그죠? So that's one of the assumptions that we should have before we practice the Dijkstra's algorithm on top of finding shortest path. Can you do this? Yes, you can. It's quite easy once you have done it. Not asking you to program, but I ask you to do maybe a practice with your own hands. Pen and pencils. Pencil and papers. Pen and pencil은 뭐야? pen and paper. And then you can just do it once. 이거 I recommend you to do it at least once. 눈으로 보면 쉬워 보이죠? 막상 글로 쓰면 패스 잊어버릴 수 있어요. So if you just draw that type of array, then you just simply practicing this loop, this pseudocode. Good? Good? Can you find a better algorithm than this? 뭐 있을 수도 있죠. 있을 수도 있죠. But idea of you try every single path, greedy algorithm, 그죠? Among all the paths, I choose the minimum one. The idea still applies. Never changes. 그죠? 어쨌든 간에 가볼 수 있는 데는 다 가보고 모든 컨비네이션은 다 해보고 그 중에 이렇게 보면 그 중에 제일 작은 놈, 그 중에 제일 작은 놈 골랐으니까. 그렇죠? 전반적인 아이디어는 변하지 않아요. What if you try to find the shortest path from every single node, between every single node? From A to every other node, maybe from B to every other node, from C to every other node. What would you do? If you want that value. Well, you might have to try this Dijkstra algorithm on every single node, which will take, it's also a high computation too. 이거 이렇게 보면 이거 running time 얼마나 될까? Time complexity, in terms of time complexity, what might be the bound, maximum bound of this worst case 하면 어느 정도나 될까? 그냥 얼핏 보기에는 얘에서 딴 애들까지 다 가야 되니까 얼핏 보기에는 number of vertices square 이래야 될 것도 같고 얼핏 그러니까 정확하게 아니라 큰 바운더리에서 얼핏 이것도 보면 n 스퀘어 정도 될 수도 있겠죠. 그렇죠? But depends on the implementation. You might be able to achieve it faster than that n square algorithms. That's what they discuss in here. So in terms of implementing, they try to implement this in programming languages. The simplest implementation is to store the vertices in the array or linked list. Linked list we haven't covered yet. will be covered in the data structure. But if you use that way, probably they say the big O of it means 이거 하면 number of vertices. Number of edges. It says running time may be I usually don't care about this. More, I could say n square. 그치? 비슷하게. It's more exact. But if you choose in some sparse graph, it means that this previous graph that we had for the example has a lot of edges between all nodes. But in case if your graph doesn't have that many nodes, sometimes there's only a few paths in it. For sparse graph, not much edges in the between. Very few edges and many nodes. It can be implemented more efficiently, storing the graph in the adjacent list using binary heap or priority queue. This will produce a running time of something like log and log n. 그냥 이렇게 보면 돼요. 이거 그냥 참고사항으로만 알고 있어요. 아까 그래프 같은 거는 이거는 여러 군데 막 많이 연결돼 있잖아요. 갈 수 있는 길도 많고 이런 경우에는 이 방법을 써서 임플리멘테이션 하면 N2인데 만약에 상대적으로 좀 적거나 노드는 많은데 엣지가 적은 그래프 같은 경우에는 좀 더 빨리 할 수 있는 구현을 좀 빨리 할 수 있다. Priority heap이나 adjacent list also coming up in next year when you guys taking the data structure. So it's just something to think of because we covered the time efficiency in the first few part of the course. Okay. 왜 너무 쉬운 거 너무 오래 해서 지겹지? 근데 방법은 참 간단한데 막상 짜오라 그러면 그렇게 쉽진 않아요. 막상 짜오라 그러면 그렇게 쉽진 않아요. 여러분들 지금 C하지? C 코र्스하지? C 하는 사람들은 아마 비슷하게 짜볼 수도 있을 거예요. 근데 아직 좀 이르긴 일러. 좀 어려워. 막상 하려고 그러면. It says, the next page says, they wanted to prove whether this algorithm is correct or not. Because type of algorithm like greedy, they try every solution. So make sure they actually have a solution. Can you prove it or not? So as all greedy algorithms, we need to make sure that it is a correct algorithm. It always returns the right solution if its given input is correct. We need to prove that too. Actually, there is a formal proof on this Dijkstra algorithm. But like it says, it's quite difficult. You can certainly take a look at it. The last page of this slide gives you the reference paper to read on, but it's going to look like a lot of mathematics. But we're gonna give you idea of how to prove this, whether this is working or not. So in order to prove this algorithm working or not, they rely on two properties. Something like triangular inequality. lemma가 정확하게 뭐라고 해야지? lemma. 가설이라고 그래야 되나? 뭔가를 가정이 있으면 가정고 그 아래 들어가는 조그만 소가정 뭐 이렇게 보면 돼요. 작은 가설. lemma 1 and 2. So this is the basic idea on how to prove your Dijkstra's algorithm. Triangular inequalities. And lemma 2 says subpath of any shortest path itself is shortest path. So if it's a part of the shortest path, then it is the shortest path. 똑같은 말 프루프하는 거 같지? 증명이 원래 이상한 말 증명하는 게 증명 아니에요. 여러분들 증명은 어디서 좀 나와요? 어디? 다시 못 들었어요. 명제? 명제가 뭐냐? A는 B다. A가 B고 B가 C면 A는 C다 뭐 이런 거? 나도 가장 싫었던 질문들이 증명하라는 질문이에요. 대학교 1학년 때 가니까 뭔 전부 다 숙제가 뭐를 증명하라. 뭘 쓸 줄 알아야 증명을 하죠. 그죠? But we're not going to discuss that. But just take a look at this. They say this is an idea for doing this. What is a triangular inequality? Triangular is what? Triangular. 그지? You can calculate the distance in the between. 어떻게 하지? 뭐 이렇게 해갖고. 이거 뭐 나오냐? 이거 하면 자동으로 나오는 거 있잖아, 정석에. 피타고라스. 그지? 피타고라스의 정의 막 나오지. 그죠? 여기 또 좀만 들어가면 피타고라스의 정의가 여기 사용됩니다. But triangular inequality, it simply means this. Okay, this is point A, B, C. So it looks like if I wanted to go from A to C, 그지? There seems to be two paths from A, B, C or AC. Right? Two. So if you look at the length of each, then it seems to be this always bigger. This always has to be bigger. How can you prove this is correct? 피타고라스의 정리 이용하면 뭐 이렇게 하고 구할 수 있는 방법 있잖아. 그러면 이거 맞죠? Triangular equality. This always holds for triangular, 삼각형. But this breaks. This is no longer true. Many examples that we saw in the previous graph, sometimes this is better. This is greater. This is what we call a triangular inequality. They break the basic property of the triangular. 그죠? So they use this property to prove that algorithm works. 그지? 완벽한 삼각형 같으면 이렇게 될 수가 없죠. AC의 길이는 AB랑 BC랑 더한 것보다 클 수가 없죠. 근데 실제로는 크다 이거야. 그 성질을 이용해서 증명을 했다라고 얘기하는 거고. 아까 전에 전 example 보면 그렇죠. 어디 한 군데 더 거쳐갔는데 더 먼저 갔죠. 더 코스트가 훨씬 낮았죠. 그렇죠? 나중에 이거 인터넷에서는 대부분 다 triangular inequality 많이 나와요. 어디를 거쳐갔는데 더 빨리 데이터를 받아. 생각 같아서는 곧바로 가야 더 빨리 받을 것 같은데. 그렇죠? 여러 가지 팩트가 있겠죠. So that's what they try to say. Lemma 2, subpath of any shortest path is itself shortest path. 이건 뭐 크게 신경 쓰지 마요. Shortest path, A, B, C가 shortest path면 A, B도 그 중에서는 가장 짧은 거리다 라고 얘기하는. 거꾸로 놓고 얘기하면 당연한 얘기예요. 그죠? 그 성질을 이용해서 프루프했다고 설명을 하고 있습니다. 그냥 참고사항으로만 알아둬요. 나도 잘 이해 못해. 너무 어려워. 실제 프루프가 증명이 되어 있는 몇 장짜리 문서를 보면 딴 나라 얘기예요. 엄청 어려워요. 굳이 읽어볼 필요는 없은데 궁금하신 분들 한 번씩 봐요. 근데 이 아이디어를 그대로 써서 증명을 하고 있습니다. So the key is to understand why we claim that anytime we put a new vertex in S, we can say that we already know the shortest path to it. It's okay. Okay. So why we use this? Why we using this Dijkstra's algorithm? As mentioned, Dijkstra's algorithm calculates the shortest path to every vertex from one source to every other node. However, it is about computationally expensive to calculate shortest path from vertex U to every other vertex using Dijkstra's, as it is calculate the shortest path to some of the vertex U. So it means in order to calculate the shortest path from one vertex to the other would take long time. It's not a easy. It's not a light type. It requires heavy computation. That simply says. Therefore, anytime we wanted to know the optimal path from some other node to some other vertex from a determined origin, we can use the Dijkstra's algorithm. Blah blah blah. Don't worry about it. Where this algorithm can be used. You guys are using it anyways. You guys are using anyways from other systems. Try to find the path from my house to Hanyang University every single morning. I live in 잠실 area. 잠실. 혹시 잠실 사는 사람? 없어? 이런 씨. 아무도 없어. 주민이 없네. So every morning I wake up, I think of the path, the driving path from my house to university. How do I do that? I might have a few options to drive to here. What might be the cost in that graph? 내가 그려줄게. 참 별의별 걸 다 그리네. 서울, 한강. 한양대 어디지? Where's 한양 University? 네, 아닌가? 여기? 오른쪽 여기? 몰라. 어쨌든 somewhere around here. My house is 잠실이니까 여기 어디? Okay. I could go here. In here, I could go here, here, I could go here, here. At least 3 paths every single morning I can choose. 여기 건대, 여기 뭐 성수대교, 여기 잠실대교. 하긴 뭐 이렇게 얘기해봐야 모르지. There are certain points that I have to go through. 그죠? Point. What is the cost in this graph in the morning time? Maybe traffic. Too many cars. The cost of taking this Seongsu Bridge is 10 minutes. Cost of taking Jamsil Bridge is 5 minutes. 10, 5. I add it up in my brain and try to find the optimum path. Oh, this only takes 10 minutes, so I choose the minimum one. So I do this every single day. I kind of running this part of the Dijkstra's algorithm in my brain. Same thing, like Google Map, 지도, mapping services. If you put one point and then go select the destination point, they usually give you the best path. Best path. Usually means the minimum time it takes. 그치? 지하철 앱에 보면 두 가지로 나오죠. Minimum time and minimum number of stations. Those type of applications is a good example of running a Dijkstra algorithm from in your programs that you use. 이 다 포인트잖아. 실제로 이 그래프도 놓고 보면 다 포인트야, 포인트. 물론 디젝스트라보다는 조금 더 발전된 알고리즘을 많이 쓰겠죠. 그래도 아이디어는 똑같죠. 갈 수 있는 모든 길 중에서 가장 빠른 길. 근데 여기서도 똑같이 에지 안에 그 웨이트가 있죠. 웨이트 뭐 이 길에서 여기 가는데 10분, 저기서 가는데 20분. 웨이트. 값이 weight. You add all those weight that gives you the cost of the entire path. I always looking for the shortest path, minimum time consuming path that I want. So that's a good example for this Dijkstra algorithm is running, as well as the internet system as well. 이거는 뭐 다음, it's the next chapter we're going to discuss a little bit on the internet technologies, how the network is being, the actual internet. Maybe this is our building, ITBT building. ITBT building. This is your smartphone maybe. It has to go to the engineering building too in order to go out to the internet. So there might be a few possible paths. From here, if there's an edge, you can go here and here. Or if this line is busy, you can take the path above, go out. So in your actual devices, desktop, smartphone, they actually find the path in this way as well. Well, they don't do it every single time, but somewhere in the core internet, there are algorithms to run like this to find the minimum path. 여기서 또 시간이 적게 걸리는 걸 하겠죠. 이건 뭐 좀 이따 나중에. Or there are another applications like biology people. They also try to do that. 뭐 나중에 예제로 나오는지 모르겠는데 뭐. 약물을 어떤 걸 먹었을 때 무슨 증상이 나타나는지를 증상을 점으로 놓고 약물도 뭐 점으로 놓고 해서 둘 사이에 막 이렇게 연관관계를 다 그림으로 그려줘가지고 그 중에 가장 빠른 길 약 뭐 먹었을 때 나타나는 증상 뭐 차차차차차 따라가는. Also, there is a type of application that you can try on biology. Try to find a mapping between the chemicals and the maybe symptoms or disease that have relationship onto. And plus the SNS is the good example of nowadays for social modeling. 그죠? 그래프 이렇게 돼 있으면 trying to find the minimum path between two friends. What is the maximum number of hops, maximum number of distance from between two strangers? 혹시 그런 연구 본 적 있어요? Later, at the end of the course, if you have time, I will bring up one slide explaining that. 혹시 그런 거 들어본 적 있어요? 나랑 아무도 모르는 사람이랑 연결이 되기 위해서 몇 명이나 거쳐가야 되는지? 6명. 어디서 봤네, 보기는. 그죠? Minimum, the small word properties. 그죠? That is also type of places that you can run the algorithm on it. 6번 하는 건 어떻게 알았어? 그건 어디서 나왔어요? 신문에서? 책? 무슨 책에서 그게 나와요? 그것도 나중에 다 이걸로 표현이 돼요. 6번. 요즘엔 6번보다 좀 작을걸? 조금 줄었을 거예요. 아마 0.5 정도 줄었을 거예요. 아마. 6번 그거는 6, 70년대 얘기예요. Anyway, here are the references that you can certainly take a look at. So he's Professor Dijkstra's original paper in 1959. 우씨, 완전 1959. 1959이면 도대체 나도 태어나기 전이에요. 한참 멀었으니까 뭐. And there are some other papers that you can certainly take a look at it for your, or if you want more details, like those formal proof that you wanted to study, then it might be the good place to look at. Okay. Any questions regarding on this Dijkstra's algorithm? I'm not asking you to memorize the pseudocode, but at least practice the pseudocode a few times so you don't forget it. Okay? Now, I'm not asking you to implement it because you're not ready yet. So, but make sure this is one way to try to follow someone else's algorithm so you can apply to it. And know the complexities. Imagine that if you try to implement this and if you try the same algorithm on top of maybe 1,000 node, 아마 이거 1,000개 디젝스트라, 1,000개, 2,000개만 해도 잘 안 될걸요? I have a data set of 얼마더라? 기억도 안 나네. 한 수천 개, couple of thousands node collected from the internet. It takes a long time to run this Dijkstra's algorithm, and it's not easy if you actually try apply on this. You need to do other tricks like maybe you need to stop somewhere in the algorithm. If you have a good enough values, you need to change a little bit. 저거는 진짜 제일 짧은 거리만 찾는데 너무 많은 노드에 너무 많은 거를 실제로 이 알고리즘을 위에다 딱 돌려보면 한참 걸려요. 며칠씩 걸리기도 해요. 잘못 걸리면. 그러니까 알고리즘을 살짝 바꿔야 될 때도 있을 수 있어요. 그냥 어느 정도 쓸 수 있는 패스가 나오면 굳이 제일 짧은 거 안 찾아도 되게 바꾼다든가. Maybe you can break out the loop in some special cases. Maybe that might be an idea of doing it. Okay. Assuming there is no questions. I'm gonna call out the attendance now.